Alright, so I'm just introducing this problem before we get started. Um, I'm using Matlab to do this because Matlab has a few apps here that are kind of nice to be able to use. You'll see like neural network stuff up here, PDE stuff, biology simulators, all kinds of things. One thing that is nice for us in this problem is that we're going to be looking at some colors, and so I'd like to take a look at a color um, some kind of a color map app. Let's see, where is it? Color thresholder. Um, well, you could probably play around with that. Um, yeah, sure. Let's give that a try. Oh, there's the color space. So let's load the image. That's what I was looking for. And I've got the P33 or P355 f1.jpg. That's the one we want to open. So this is work with Professor Cooley in biology. Okay, good. And so the problem is we have these photos of these flower petals, and the flower petals the colors are really just yellow and red. And so what we'd like to do is somehow extract, we'd like to be able to tell which of the um, which part of the petal is red and which part of the petal is yellow. We'd like to separate those. And so what's nice about this app is that you can see what the colors look like in different color spaces. And so I didn't want to talk too much about color space, but there is we usually use like a red, green, blue color space, and you can kind of see how the data is separated in the red, green, blue space, right? But there are other color spaces, and it turned out just through some experimentation, we found that in this problem, if we use the LAB space, that the colors seem to separate a lot better than in the RGB space. Okay, um, why would that be? Well, we can try to cluster this in LAB space, but actually we're not even going to use the L space. We're just going to use A and B, and it's going to turn out that the colors separate very nicely in AB space using k-means. And so what we're going to do is we're going to load this image into either Matlab, Octave, or Python, and then we're going to convert the colors from RGB to LAB, and then we're going to strip off the L from the LAB, and then we're just going to use AB. And so what we're going to do then is we'll have this big matrix of AB space, right? And so each point corresponds to a point in A and a point in B. And so these are your coordinates, two-dimensional coordinates for every index in the image. Does that make sense? And so you're going to have a huge array of points in two dimensions AB space that we're going to cluster. And we're going to do that in using k-means. Okay, and so I'll pause here and we'll go ahead and open up, maybe we'll just go ahead and open up Octave instead of Matlab just to see how it looks. All right, so I'll be back in a moment. All right, we're back. So this is Octave, and I've already got the file open. Just ignore this stuff on the left panel here. But I will say that we do need to have some packages from Octave in order for this to work. One of them is the image package to do the color conversion, and the other is the statistics package in order to do k-means. Now, if you haven't, if these are not loaded already, you can go into the command window and you can type package install, and then for example, if you needed the stats package, you could say forge statistics, and Octave will go ahead and download the package and then install it. Okay, if you're not sure what packages you have installed, you can just type in package pkg and list. So I've already installed a few of these. I've got I had to install IO when I first installed statistics. So you may have to install IO as well. You'll get an error if it's not there. And then I installed the image package and the statistics package, and they were all done the same way. That is pkg install, if I can spell. This is from the Forge distribution, and then it's like image or IO or statistics. Okay, and then it'll download and get your package ready. I should say, after you've done that, you still have to do one thing when you're going to use these packages for the first time, and that is you have to say package load statistics, package load image. So I've written this on the script file so I remember. And so let's just go through this script file real quick. I like to clear out my variables before I start just to make sure that there's nothing old hanging out. And so this first line here, xmap is mread. Yeah, this is just reading in the JPEG file. I should say that this Octave Online doesn't like to make an image for some reason. So you might get an error message about showing the image in Octave Online, but it works for either Octave at home or Python. We'll get to the Python version in just a sec. Okay, so what's going on next on line 25 here? We're just converting color space. So X is currently RGB, and then we're converting it to LAB. And then I like to figure out how many rows and columns I'm going to have so I can use formulas for the rest of these. So if I change the image size, it'll automatically change for me. And so what's going on here on line 28, maybe I'll even put a comment here. This is stripping off the L channel. Just use AB. Okay, so and then then like I said, our data for clustering is now the number of rows and number of columns, right, by 2, because the 2 dimensions here, right, are the A and the B channels. So if you think of your image, right, as being like 10 by 12, and each of those 10 by 12 values has an A value and a B value, then you can think of that as a 10 by 12 array of 2-dimensional points, right? So that'd be 120 points in 2D. And so that's what's happening here. Y2 is number of rows times number of columns by 2. And so this is the data set that we're going to be clustering. Well, of course you can see that. And so the 3 here is the number of clusters, of course. And so then I just reshape the index. The IDX is the index of the outcoming points. And so that's going to be a vector of the same size as the number of points. And each of those indices will be an integer from 1 to the number of clusters. Okay, C is returning the location of the clusters for each cluster. So that's going to be a 2 by 3 or 3 by 2. I'll have to check. So 3 clusters in R2 is what we're saying. And the distance error here is the distortion error, actually, of each of the 3 clusters. Okay, and so now to visualize what's happening, we're going to reshape the index vector. Remember, the index vector has integers from 1 to 3. And so Z is going to be an array that is n rows by n columns, and each of the values stored in this matrix corresponds to which cluster we're on. Okay, so that's how we're visualizing the image. Good. So let's go ahead now and run this file and see what happens. I think it's just going to run without stopping, so let's see. Good. So, of course, it runs very, very quickly. So what you're seeing here is the original image, like we were talking about before. And we wanted again to be able to distinguish between the colors there. And you can see, I'll try to put this right underneath, maybe not, so you can see what happened. So you can see that the clustering works really, really well. It looks like we got all the red taken out. And so this is a nice example of using k-means clustering to do image segmentation, be able to identify which clusters are where. Good. Now I should say we don't know which cluster belongs to which color yet. So for example, the background could be cluster number 3, or it could be cluster number 2. It could be cluster number 1. The red part might be cluster 1, 2, or 3. But that doesn't really matter, right? Until you actually need to extract those data points, because right now we just want to be able to tell the difference between red and yellow and white. Good. And so that's the k-means using Matlab. All right, I'll stop here.